Hello, and welcome to Lecture 3 of CS 182. Today, we're going to talk about bias, variance, and regularization. So, the question we're going to start with is following up from last time. Last time we learned how we can train models with gradient descent to perform classification. Today, we're going to ask, will we get the right answer? So if we follow the recipe, if we follow the machine learning process outlined in the previous lecture, how will we know if our model is going to do well, if our model is going to get the right answer? So to understand this, let's revisit empirical risk and true risk, which I discussed briefly at the end of the previous lecture. So we're going to be working with the 0-1 loss, which this time I've written correctly on the slide. So it's an indicator for whether you got the wrong answer. So the loss is 1 if you got the wrong answer, and 0 if you got the right answer. Risk, as we discussed last time, is the probability that you will get it wrong. So if we imagine that there is a generative process, a process that gives rise to our data, for example, our images are sampled from some distribution over images, and our label is then sampled from the true distribution over labels, then we could ask the question, how likely is it that our learned model, f theta of x, is wrong? And the expected value of the 0-1 loss quantifies this, right? So the expected value of the loss, which is 1 if wrong and 0 if right, is basically the probability that you'll get it wrong. This might seem like kind of a roundabout way to express the notion that you want the probability of the wrong answer, but the nice thing is that you can generalize it to any other loss. So the 0-1 loss is the one for which the notion of risk semantically makes sense, but you could imagine a notion of risk which is the expected value of any other loss, such as negative log likelihood. And that's where the definition of risk comes from. Risk is just defined as the expected value of your loss under the distribution that gives rise to your data. Critically, this is not the same as the loss on your training set, because your training set is a sample-wise estimate of this expected value. So during training, you don't generate new samples from P of x, you just have your data set D. And that's called the empirical risk. The empirical risk is the average of the loss over your data set, which you can think of as an approximation to the true risk. Now we could ask, is the empirical risk a good approximation to the true risk? Well, it's an unbiased approximation a priori. So if I just give you a theta and I ask you, tell me what the risk of this theta is, and you evaluate the empirical risk, that will be an unbiased estimate, meaning that if you had a variety of different data sets in expectation, they would all come out to the same, to the right value. The problem is that you're actually going to be using the empirical risk to select the theta in the first place. So the theta is not chosen independently of your empirical risk estimator. You're actually choosing theta to minimize this quantity. And when you do that, you're liable to minimize the empirical risk without actually minimizing the true risk. And that's actually going to be the topic for most of the discussion for today's lecture. So if this notion seems a little opaque to you right now, if this is not quite clear, don't worry, we're going to talk about this a lot more today. So is the empirical risk a good approximation? Well, not always. So in supervised learning, we're usually doing empirical risk minimization, which means that we're minimizing the average loss on our training set. And this is not quite the same as the true risk minimization. And when they are not the same, we sometimes refer to this as overfitting. So overfitting refers to the case where the empirical risk is low, but the true risk is high, which means that you have a model with parameters theta that have a low loss on your training set, but the expected loss under the entire data distribution, under the distribution over all possible images you might get, is actually not low. It's pretty easy to see how this could happen with a really simple one-dimensional example. So, and this is the same example that I gave in the previous lecture. Let's say that you have these black dots representing your training set. So empirical risk minimization would try to fit a curve that is as close as possible through those points. The true function is given by the straight line. So the data consists of that true function plus some additive noise. Lots of data has additive noise. There's some additive noise in everything. The empirical risk for the blue curve is extremely low, but its true risk is actually very high. So that's because your blue curve did a good job of fitting the data, but it did a little too good of a job. So this can happen if your data set is too small, if essentially the training points that are given to you don't fully specify which function you should get. And this is almost always the case in machine learning, particularly in deep learning, where we're going to be dealing with functions that have perhaps millions of parameters, often more parameters than there are training points. This can happen if the model is too powerful, it has too many parameters or too much capacity relative to the size of your data set. The opposite problem is something called underfitting. Underfitting is when the empirical risk is high and the true risk is high. So in underfitting, the empirical risk is representative of the true risk, but they're both bad. And this could be the case if the model is too weak, if you have too few parameters or too little capacity. Like in this case, where the true function is probably a curve, but you're trying to fit that true function with a line. This can also happen if your optimizer is not very well configured. For example, if you have a bad learning rate. If you're essentially not doing a good job of actually minimizing the empirical risk, even though you could. And this actually happens quite often in deep learning because the optimization problem in deep learning is itself quite challenging. So for logistic regression, which we covered last time, the optimization problem is actually not too bad. But for deep neural nets, which we will cover in the next few lectures, the optimization problem can be very difficult, and you can actually get underfitting even though you have a very high capacity model, simply because you are not able to minimize that loss effectively for that model, perhaps because you chose the wrong learning rate or the wrong type of optimization algorithm. All right, so that's kind of the higher level conceptual view of things, but let's do a little bit more formal analysis. Let's try to actually mathematically understand what is overfitting and what is underfitting exactly. Can we put some equations on it? Last time, in the previous lecture, we discussed classification. That's the problem where you go from an input, like an image, to a label or a probability distribution over labels. This time, we're going to instead focus on the problem of regression. Regression means that you are predicting a continuous variable or a continuous distribution based on your input. All the stuff I'm going to discuss applies to classification also, but it's just a little bit simpler to derive the math for the regression setting. So regression is basically curve fitting. It's like you have some continuous or discrete inputs, and you have a continuous output, and you want to predict that continuous output. So instead of predicting a categorical label, cat versus dog versus elephant, you're predicting a real number like y. Maybe you're predicting how big is the dog, how much does it weigh, things like that. How expensive is the house? So if we want to adopt the probabilistic approach, which we took in the previous lecture, then in order to do regression, we need a probability distribution over a continuous valued output y. So y is now not a label, y is a real number. There are many probability distributions that we could use to represent real numbers, but a very simple choice, which hopefully you've learned about in one of your statistics or probability theory courses before, is the normal or Gaussian distribution. So the normal distribution is defined by two parameters, a mean and a variance. But of course, we want to solve a prediction problem. We want to predict a distribution over y given x, right? So in our case, we're going to have a conditional Gaussian distribution, which is to say we're going to have a Gaussian whose mean and perhaps it's whose variance are themselves functions of x. So they're not just numbers, they're actually functions. So what I have written on this slide is the equation for the log probability of a normal distribution. This is not an equation that I made up. You can just open up a probability textbook or go on Wikipedia and you'll find this equation. Sometimes you see it written out as a density. Here I have it written as a log density. It looks like a big equation, but it really consists of three simple things. The first thing, this negative 1/2 f of x minus y sigma inverse f of x minus y, is basically just the difference between f of x and y, but under a particular norm defined by sigma. So it's basically how close is the mean f theta of x to the true label y. The second term, negative 1/2 log of the determinant of sigma, basically tries to get the variance to be lower. So it's saying, well, if you can fit the true y's accurately, try to use a lower variance. And then the third term is a constant that does not depend on x or y. If we don't bother learning sigma, if we just fix sigma to be the identity matrix, then the normal distribution reduces to the square of the difference between f theta of x and y. So it's just negative 1/2 f theta of x minus y squared. That's very, very simple, plus some constants. That's very simple. So oftentimes when we talk about regression, the particular distribution that we choose is actually a normal distribution, but we choose sigma to be the identity, and then the log of this normal distribution just corresponds to the square of the difference between f theta of x and y, which is very simple. We don't have to do this. We could actually learn sigma theta of x. But for the derivation in this lecture, we won't do that. We will just use f theta of x minus y squared. But I just wanted to make it clear that this is not just a made-up objective. This is actually the log probability, or the log density, for a well-defined distribution. Just like we used the softmax distribution in the previous lecture, we're using the normal distribution here for regression. Now, after we make this simplification, where we set sigma of x to be the identity, this is the same as the mean squared error loss. So if you've ever heard MSE loss or mean squared error loss, it just says the loss for a particular point x and y is negative 1/2 f theta of x minus y squared. That is also the log probability for a normal distribution with the covariance sigma set to identity. So that's quite neat. And mean squared error loss, of course, is very simple. Hopefully a lot of us are familiar with this. If you have a linear model, then minimizing the mean squared error loss just corresponds to conventional linear regression, which is usually the first statistical estimation method that most of us learn in a probability theory or statistics class. So it's a bit easier to analyze mean squared error, but we can analyze any other loss function as well. So the analysis I'll present will be for mean squared error, but keep in mind that it can be extended to other losses. Okay, so that's what we're going to work with. We're going to work with mean squared error, which is the log probability of a normal distribution. And let's recall that overfitting is when the empirical risk is low, but the true risk is high. That means that the average loss on your training set is low, but the actual expected value of the loss under your training distribution is high. This can happen if the data set is too small. It can also happen if the model is too powerful, if it has too many parameters or too much capacity. Like this polynomial example that I showed before. Underfitting, that's when the empirical risk is high and the true risk is high, like the straight line fitting example that I had before. And this can happen if the model is too weak, if it has too few parameters or too little capacity. And what we're going to understand next is how we can connect up actual equations for that mean squared error loss to these two phenomena. By the way, underfitting can also happen if your optimizer is not configured well, for example, if you have the wrong learning rate. And we'll actually talk about that a lot more in a future lecture when we discuss optimization methods. All right, so let's try to understand overfitting and underfitting more formally. The question here is, how does the error change for different training sets? Why different training sets? Well, we'll see in a moment why this makes sense, but intuitively, we'd like to do our analysis in such a way that we understand the overfitting or underfitting tendencies of our algorithm somewhat independently of which particular data set it's trained on. Because with a given data set, we could get lucky. We could just luck out and happen to get the data set where our crummy learning algorithm happens to get a really good solution. We want to know, on average, for data sets sampled from a particular data distribution, will our algorithm produce the right answer or not? So here's why this question could be important. Let's say that this black curve is our true function. So this is the function that we're trying to fit. And these blue dots represent a particular training set. And when I fit my model to that training set, I get the orange curve. So what is my model here? Well, maybe my model is linear regression with polynomial features. So it's like theta times x plus theta 2 times x squared plus theta 3 times x cubed, etc. Polynomial regression, basically. So maybe I'll get this orange curve. Not a very good solution, right? This is a very bad solution. Is this solution overfitting or underfitting? Take a second to think about that. Remember, overfitting is when the empirical risk is low, but the true risk is high. Underfitting is when they're both high. So is the empirical risk low? I think it is, because the orange curve goes straight through the blue circles. Is the true risk low? No, the true risk is quite high because the orange curve is very different from the black curve. So this is overfitting. Now imagine that I have a different set of blue dots. So I have the same true function. The learning problem didn't actually change. The distribution over x and y also didn't change. I just had a different data set, sampled from the same distribution. So maybe if these dots were images from Flickr, maybe in the first graph I took 20 images off of Flickr randomly. In the second graph I took a different set of 20 randomly from Flickr. Remember, our goal is to understand the error that our algorithm is likely to produce independently of which particular data set it got. So we're not trying to determine if we got lucky with just the right data, we're trying to determine if our algorithm tends to overfit or underfit. So if you imagine the same kind of polynomial regression for both of these, for the second and third data sets, see the blue dots are in a different place, but they're still in the black line, well, maybe these are some polynomial regressions you might get. They're all overfitting. They're all bad. They all have low empirical risk and high true risk. But critically, all of the orange curves are different from one another. And that's a very important observation. When we are overfitting, in general, we will see that different training sets, even though they come from the same distribution, will lead to very different solutions. And if we think about this for a second, this is actually kind of inevitable. Because we have to get, in order to overfit, we have to get low empirical risk and high true risk. Low empirical risk means that the orange curve has to go through the blue dots. High true risk means that it can't match the black curve. So as we move the blue dots around, if the orange curve stays the same, that means that the orange curve has to match the black curve, because you can't move those blue dots around and have the orange curve go through them if it's not actually matching the black curve. So if we're getting overfitting, that means the orange thing goes through the blue dots, and that means that it has to be in different places when the blue dots are in different places. So this issue, where you get a different solution for different training sets, is actually kind of inevitable if you know that you're getting overfitting. On the other hand, if you're getting underfitting, that means that your empirical risk is high and your true risk is high. You're not getting a good fit. So maybe you have a linear function that you're fitting to this curve. The linear function will be a bad fit, but it's not going to vary nearly as much between different training sets. In fact, if you aggregate all of these data sets together, so here I just took all of the blue dots in all three examples and just put them on one graph, the linear fit to this aggregated data set will probably look pretty similar to the fits that it had to the individual data sets. Like the third one is a little off, but mostly they're pretty similar. And this is also, in some ways, inevitable if we know that we're getting underfitting. Because if we're getting underfitting, that means that our model is not powerful enough. It doesn't have enough free parameters to fit our function accurately. So if it doesn't have enough free parameters, that means it's not utilizing all the information that's present in the training set. So as the training set changes, it's not going to change very much because it's not pulling out all the information anyway. It can't make use of all that information. So when that information changes, it doesn't change very much. So in overfitting, the training data is fitted very well, the true function is fitted poorly, and in general, the learned functions will look different each time if you use a different training set, even though it comes from the same distribution. In underfitting, the training data is fitted poorly, and the true function is fitted poorly. And the learned function looks similar even if we pool together all the data sets. So that's the intuition. Now let's make this more mathematically precise. What we're going to do is we're going to write down the expected value of the error given a distribution over data sets. There's an important subtlety here. We're not taking an expected value with respect to x or y. We're going to be actually taking an expected value with respect to the data set D. So our data set is produced according to some distribution, right? We assume that we sample images according to p of x. We sample labels according to p of y given x. Our data set is just a collection of x's and y's, which means that we can write down a probability of D. So we can say P of D is just the product of the probabilities of the individual data points that comprise D. All right, so if we can write down a probability over D, that means we can take an expected value of a function of D. So we can say, well, what is the expected value of the error between f theta of x and y, where f theta of x here is trained on d, but d is a random variable. Okay, this is a little weird. It might take a second to wrap your head around what exactly this means. So this is not an expression that measures the average error for a particular function of theta of x. It's actually measuring the expected error of your training algorithm. So for every value of d, you get a different f theta of x. To make this a little more explicit, what I can do is instead of writing it as f theta of x, I'll write it as f d of x, just to emphasize that this is really a function of d now. So d goes in, your learning algorithm works on that d and produces a theta, and then we're going to look at the error of that. So it's like a meta-level thing. It's like we're asking, in expectation, if I give you infinitely many data sets, and you train on each of those data sets separately, what will your error be on average? So this is trying to quantify how good your learning algorithm is. It's not trying to quantify how well you did on a single given learning problem. And by the way, this is a theoretical exercise. So in practice, when we do machine learning, we only get one training set. We don't actually do this in practice. This is just analysis. This is just some math that we're going to do to try to understand how we can get low empirical risk, but high true risk. So in practice, of course, you don't actually compute expected values over data sets. That would be crazy because you'd need a huge number of data sets for that. So this is a theoretical exercise. And just for notational clarity, I'm going to write f of x in place of y. So f of x is the true function, f d of x is the function I get from training on d. Okay, so let's write out this expected value, right? So this is just from the definition of expected value, just from your introductory probability theory course. The expected value of some function is just a sum over all the values of your random variable of the probability of that value times the value of that function. So our function is the squared difference between f d of x and f of x. Our probability is p of d, which I have defined above. So that means the expected value is a sum over all possible data sets of the probability of that data set times the squared difference between f d of x and f of x. Okay, if this looks weird, it is kind of weird. Like summing over all possible data sets, like, whoa, that's a crazy thing to do. Again, this is a theoretical exercise. This is machine learning theory. It is not an actual thing we do in practice, but it will really help us to understand why our algorithm might sometimes produce the wrong answer. Okay, so this is our expected value of our error. Just as a quick check, why do we care about this quantity? We care about this quantity because it is quantifying how wrong our algorithm will be on average. Independently of the particular data set we got, on average for this distribution, how wrong will our predictions be? Okay. So let's analyze this quantity a little bit further. We care about this quantity because we want to understand how well our algorithm does independently of the particular random choice of data set. And this is very important if we want to figure out how to improve our algorithm. So overfitting is going to be when, for different data sets, our fd of x is going to look very different, right? All the data sets here come from the same distribution, the same true function, but the orange curves for each of them are different, which means that the fd of x for every d is different. Underfitting is when the orange curve for every data set is pretty similar, not identical, of course, but pretty similar, and pretty bad. So what we can do is we can take this expected value of the error and we can break it up into two terms. And we can actually assign blame to those terms. We can blame one of them for overfitting and we can blame the other one for underfitting. So for a little bit of notational convenience, I'm going to use f bar of x to denote the expected value of fd of x. Let's be careful in understanding what this means. F bar of x is essentially the average over all possible functions you would get for all possible data sets, weighted by the probability of those data sets. That's not to say that fd of x is what you would get if you had infinite data. That's not what it's saying, because every individual fd of x is still fitted to a particular finite-sized training set. but then you're just averaging their predictions together. So if you're not sure why I'm introducing this, don't worry, it'll be clear in a second. But make sure you understand what f bar of x actually means. If you're not sure, maybe pause the video or ask a question. Okay. So what we can do next is we're going to do some algebra. We're going to take this equation for the expected error, and inside the norm, inside that square, we're going to subtract f bar and add f bar, right? If you subtract something and then add back in, that's just 0. So you can always put in like minus f bar plus f bar. And then what I'll do is I'll put parentheses around the first two terms, and I'll put parentheses around the third and fourth term. So I've basically rewritten my error, which is f d of x minus f of x squared, to be f d of x minus f bar of x, in parentheses, plus f bar of x minus f of x, in parentheses, and then that whole thing squared. I didn't change anything, I just introduced an additional term, but those two terms cancel, so they're out to 0, and I put some parentheses in there. But now what I'm going to do is I'm going to distribute the square. So I'm going to actually evaluate the square of this quantity. So when you have something like x plus y squared, we know that ends up being x squared plus y squared plus 2xy, right? So I have my first term, f d of x minus f bar of x squared. I have my second term, f bar of x minus f of x squared. And then I have the cross term, which is 2 f d of x minus f bar of x transpose f bar of x minus f of x. The transpose is just if this is multivariate. If this is univariate, it's just multiplication. And I think I have a small typo on this slide. This should actually be a plus, not a minus, but it doesn't actually matter. Okay, it doesn't matter because that third term actually ends up canceling out. So let's look at that third term, the one on the last line. It's the product of two things, f d of x minus f bar of x, and f bar of x minus f of x. Now, f bar of x minus f of x doesn't actually depend on d. Right? Neither of those things have a dependence on d, so we can take them out of the expectation by linearity of expectation, and that's what gives us the equation at the bottom. Now, the first term is the expected value of f d of x minus f bar of x. But f bar of x is itself the expected value of f d of x, so it also doesn't depend on d. So then you have the expected value of f d of x minus the expected value of f d of x. So this first part just becomes 0, and 0 times anything is 0. So the whole third term actually cancels out. If it's not clear to you why that happens, you can consider pausing the video and rewatching that part again. Think about it a little carefully, maybe work it out on a piece of paper, or if you're watching it live, please just go ahead and ask a question. All right, so the third term cancels out, leaving us with just those first two terms. So let's look at those first two terms. We have the expected value under P of D of f d of x minus f bar of x, plus the expected value under P of D of f bar of x minus f of x. So the second thing, the stuff inside the expectation doesn't actually depend on d, so we can just get rid of the expectation altogether. It's just the difference, the squared difference, between the average over all of your predictions, which is f bar, and the true function f. So it's like that thing in the top right of the slide. We call this the bias. Technically, this is the squared bias. So the bias is f bar of x minus f of x. When you square it, that's the squared bias. So the bias essentially quantifies how far off is the average prediction you get from the true function. So in this case, the bias is pretty high. So the bias is kind of that error. This error doesn't go away no matter how much data we have, right? The bias is just quantifying how underparameterized we are in some sense. The first term is the variance. Notice that this first term doesn't actually have f of x in it. So this is, regardless of what the true function is, this is quantifying how much does our prediction change with the data set. So that's just quantifying this variability. Now, of course, your predictions do depend on the true function in the sense that the true function produces the training data, but this is not error to the true function. This is just how much does fd of x vary for different training sets? How much does it deviate from its average value? So the full error is just the variance plus the bias, well, bias squared. And these two terms actually account for overfitting and underfitting. So if the variance is too high, that's the setting in the lower left here. If the variance is too high, then you have too little data or too complex of a function class or something like that. And this is overfitting. So overfitting means high variance. If the bias is too high, you have an insufficiently complex function class. So the problem is not that you get a different function depending on the data set, it's just you just can't get an accurate function, period. And that's underfitting. And once we recognize that our error consists of variance and bias, then we can recognize that getting an accurate solution, getting an algorithm that works well, requires regulating the trade-off between bias and variance. So if we have too much variance, then we need to reduce variance and maybe increase bias a little bit. If we have too much bias, then we should decrease bias, which could mean increasing the variance a little bit. And it's very important to understand which term is big and which term is small, because many of the troubleshooting techniques we have for reducing variance will actually increase bias and vice versa. So if we get it wrong and we try to fix our algorithm, maybe we think our variance is high, but in fact our bias is high, we'll actually exacerbate the problem. So it's really important to understand if you're getting the wrong answer, is it because of variance or because of bias?